Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're once again tackling the Carnot cycle, Carnot cycle being the ideal cycle that is a very good foundation for you to be able to tackle any other cycles that will come along afterwards, so the Otto cycle, the Rankine cycle, and so forth. If you recall, the Carnot cycle has two isothermal transformations, one isothermal expansion, one isothermal compression, and two isentropic transformations, one isentropic expansion, one isentropic compression. Right? On this problem, the particularity of this problem is that we're given the temperature boundaries, but we're not given one state completely defined, whether this one, or this one. Okay, we're only given the pressure of one state and the two temperature boundaries. So that means that we cannot find volume or masses for that state for the states. Okay, so this means that we need to find relationships between the things to be able to define the state as best as we can, but we won't be able to completely define them in the sense of us finding volumes and masses. Okay, so this is the tricky part about this problem. Let's read problem statement, which says a Carnot cycle operates with air as a working fluid. So first things first is air as a working fluid. We can take air to be approximately an ideal gas. And that already simplifies a lot of things for us. But then again, Carnot cycle, you would always expect an ideal gas, or else we're going to run into some problems on the analysis when we look at isotherms and all that. The temperature limits of the cycle are 500 Kelvin and 310 Kelvin. So the upper limit is 500. So that means I can already put here on my cycle 500 Kelvin and 310 Kelvin. The pressure at the start of the heat addition process is 350 kilopascals. So there's a pressure that's 350 kilopascals. 350 kilopascals. And this is on the beginning of the heat addition process, the start of the heat addition process. If you guys recall, the heat addition process occurs on the isothermal transformation. So this is the heat addition process, heat in, and on the isotherm compression, we have our heat rejection phase. So this is heat out. So this is saying that right here, before on the start of the heat addition process, we have the pressure of 350 kilopascals. So let's go ahead and give names to these guys. Let's say this one is number 1, state 1. This one here is state 2. This one down here is my state 3. And this guy over here is my state 4. Okay, so we're saying that P1 is 350 kilopascals. Note how that's not trivial, right? That's not something that is explicit on the problem. You actually need to make sense of what's happening and to know the Carnot cycle to be able to place this information in the right place. And the volume doubles in this process. So the stage process is on the heat addition process. So that is, as we're going from 1 to 2, my volume doubles. Okay, what is that saying? Mathematically, we can write that as, well, the volume of V2 is twice the volume of V1. Right? So twice the volume of V1. That's how we can mathematically express that information. Take the heat capacities as constant values at room temperature. This is another important thing. Okay, so we're considering Cp and Cv as constants at room temperature. So we're going to take Cp's and Cv's at 300 Kelvin, which simplifies in a lot of ways the analysis of the problem. And we're going to talk about that as we go. We are to calculate the mass of air required to produce the work output of 1 kilowatt if the cycle is repeated 5,000 times per minute. Okay, so we have a cycle that's repeating this cycle. We go around, let's go yellow. We go 1, 2, 3, 4 back to 1, and that's one cycle. Okay, and we're doing 5,000 times for every minute. So we can write that down as this is 5,000 rotations per minute. We can think of it that way. Rotations being one cycle. And we can put this as perhaps 5,000 cycles per minute, like that. Okay, whatever rocks your boat. And we want to find what's the mass of air required to output 1 kilowatt. Okay, so that's little energy we would expect, little mass is needed, little mass of air. We also want to calculate the lowest pressure occurring in the cycle. And note, again, this is not trivial, because to know that, we actually need to know the Carnot cycle, and we can note that we can read the pressure of the y-axis, right? So 1 is the highest pressure, 2 is the second highest, 4 is the third highest, and the lowest, or the fourth highest, I guess, is pressure 3. So part B is asking us, what is pressure 3? Here, what is pressure at 3? Okay. And then finally, what is the heat added and heat rejected per cycle? So what is this guy every time we go around once? And what is, what is this guy every time we go around once? Cool. So to be able to answer first part A, what's the mass required to output 1 kilowatt? What I'm first going to determine is how much output do I get when I go once around the cycle. So if I do this once, from 1 to 2, 2 to 3, 3 to 4, 4 back to 1, if I complete the cycle once, what is the energy output that I get? So how much energy per cycle? Right, so I'm trying to find something like joules per cycle, something like that. Okay, because if I do that, once I have that information, then I can relate this back into the amount of times I go over the cycle, and then I can find out the power, and with that power I can find out the mass that required for that power. Okay, so let's start by that. So what I need to do is find what's the work that this guy outputs. So what is my work output? And of course, if I'm going around the cycle, that's just a sum of all the works around the cycle. So it's the work from 1 to 2, plus the work from 2 to 3, plus the work from 3 to 4, and the work from 4 to 1. If you're already used to Carnot cycles, you know that there are a lot of symmetries that happen, and this is not going to be any different. And the first symmetry we can look at are the symmetries between the adiabatic processes, because remember that these guys are not only isentropic, but they're also adiabatic, right? And if they're adiabatic, that means that our heat is 0, right? So adiabatic, let's put from 2 to 3 and 4 to 1. We have adiabatic, and that means, so therefore, my Q is nil, right? 0. Why is that important? Because think about it. If we know that delta U equals Q plus or minus work, depending on how you use the sign convention, and we know that our Q is 0, then if this guy is nil, then obviously delta U will be equal to work, right? Plus or minus depending on convention. But why is this important? Because delta U on an ideal gas, it's a property of my delta T, right? It's a function of my temperature. And we know that we can actually do the following. If my delta U from 2 to 3 is CV times delta T, and remember this comes from the definition of CV, and we're integrating over a interval from 2 to 3. And this difference here is a difference as I go from 2 to 3, then this is just equal to my CV times my T3 minus my T2. Okay, I don't know the value for this. We could calculate it, that's fine, we have CVs, we have the delta T's, but note the following. The other one, the one as we go from 4 to 1, that will also be CV delta T, right? In this case, the delta T is my T1 minus my T4, final minus my initial. But it just so happens that my T1 is the same as my T2 because it's an isothermal transformation. And my T3 is the same as my T4, again, for the same reason. So I can substitute any of these top guys here by the other. So I can write this as CV times, and when I have T3, I can write T4. When I have T2, I can write T1. Okay, so note that this is exactly the same magnitude, different sign, right? So this is negative. So you can rewrite this again if you want to as negative CV times T1 minus T4. Okay. So what we show with this is that the delta U as we're going from 2 to 3 equals negative the delta U as we're going from 4 to 1. And because remember that because my work equals my delta U, then we can conclude that the work as we're going from 2 to 3 equals negative the work as we're going from 4 to 1. So these guys are going to cancel each other, right? So I can substitute this here when I'm summing everything up. I can substitute, for instance, this guy here. I can write this guy as negative 4 to 1, and that obviously is going to cancel out these guys here. Okay, so already we can get rid of two of the work we're trying to find. We're just left with work from 1 to 2 and from 3 to 4. Okay, so work output, therefore work output is just work from 1 to 2 plus work from 3 to 4. Okay, now from 1 to 2, 3 to 4, we have isothermal transformations, both of them, right? Isothermal. What does that mean? Well, it means that, if you remember, the definition of work is PdV, the integral of PdV over any process that we're looking for. So in this case here, we can look at 1 to 2, or we can just leave it as generic. I guess let's just leave it as generic for now. And because it's an ideal gas, we also know that PV equals mRT, M or N, depending on how you're using it. So I can say that, okay, so the integral work is going to be the integral of mRT divided by V, dV, right? And this guy is a constant because the mass is not changing, and the process R is a constant, it's not changing, obviously, and the temperature, because it's an isothermal transformation, is not changing. So therefore, this can come out of the derivative, and we're left with the integral of dV over V, and we can go ahead and do mRT, and this can be T, for instance, if we're going from 1 to 2, this can be T1 or T2 because they're the same, right? Times the natural log of the ratio between the volume. So the volume, let's put volume final, divided by volume initial, because we didn't allocate if it's 1 to 2 or not. Okay, so I can write my work from 1 to 2 and from 3 to 4 like so. So work from 1 to 2 will be mass R T1 or T2, doesn't matter, same thing, natural log of V2 over V1. Okay, and likewise I can write, let's do blue, from 3 to 4, same thing, right? Mass R, this time T3 or T4, same thing, natural log of V4, the final one, divided by my V3, which is my initial one. All right, note that we don't have, out of this first equation here, we don't have the mass. And that's all right, because that's exactly what we're looking for in part A. But we do know the constant, we do know the temperature, it's 500. And we don't know the volumes, but we know the relationship between the volumes, right? Because we know one is double the other. So what I can do is say, okay, so therefore, if I take my work from 1 to 2 and divide everything by the mass, okay, both sides by the mass, I'm going to get this like kind of specific work, right? How much energy per unit mass this process is requiring or outputting. So in this case here, we have R, and we can sub in R if you want to already, but you don't have to just for now. T1 that we know as well. And the natural log of, remember V2 is just 2 times V1, so V1 over V1 which means that this is just natural log of 2, right? So I can rewrite this one more time as R for air to 2.87. This is R for air at 300 Kelvin. Temperature 1 is 500 Kelvin. And then the natural log of 2. Okay, quick and easy. What about on this bottom guy here? Well, same thing applies. We have everything, except we don't have a relation for these two guys yet, right? So we have to find a relationship for V4 and V3 so that we can move on with this calculation here to find the work from 3 to 4 per unit of mass. Okay, everything else is going to be the same, so we're going to have 2, 8, 7. Temperature 3 and 4 is 310 Kelvin. And then we have the natural log of the two volumes that we don't know just yet. So what we need to do now is find exactly what are the relationship between these volumes here so that we can find the work output there, so we can find what's the work per cycle, which is what we're trying to find from the beginning. To do that, we're going to go back to our diagram. Where is it? Here it is. I'm going to go ahead and copy this so we can use it down there. And we're going to note the following. As we're going, so remember that we're trying to find things for this and this, but at the moment we only have information for these two guys here. So what I'm going to do is precisely use this information here from this guy to find out things for this guy, and I'm going to use this information for this guy to find things for this guy. Okay, we're going to note that as we're going from 2 to 3 or from 4 to 1, we have a set trifecta. We know it's an isentropic process. Entropy does not change, and this is by definition because of the Carnot cycle. We also know we're using constant CPs and CVs. So heat capacities are constant. And we're dealing with air and approximating air to an ideal gas. This may all seem far-fetched, but in real life, obviously Carnot cycle is not applied in real life, but in real life, these approximations are most of the time okay, depending on what you want to find. If you're not looking for precision, for a lot of cases, this is not as far-fetched as it may sound. Okay, and if we have these three things, then we know that there's a relationship between 2 and 3, or 4 and 1, right? Whenever we have these three boxes ticked, then the pressure of any state, let's put A, times the volume of the same state to the K equals the pressure of state B times the volume of state B to the K. What is K? If you recall, K is just a ratio between CP and CV. And check out this, do a little bit. This guy here means that this is going to be valid. Okay, so this relationship here exists. But, however, we need this guy here because if not, this K changes. Okay, so this equation would not be true if my CPs and CVs were not constant. Because remember, CPs and CVs, they are a function of temperature. They change with temperature. So as we're going from, for instance, if we're talking about, let's go back to our problem here, P1, V1 to the K, P2, V2, right? P2, V2 to the K equals P3, V3 to the K. If we are dealing with, we're considering the change in CPs and CVs, then this would not be true because my K would have changed as we're going from, this is 500 Kelvin, and here we would be having a K in respect to 310 Kelvin. Okay, so this one here will be closer to 1.4. This one here would not. Okay, so that's why we need a constant CPs and CVs to be able to apply this relationship here. And then finally, this guy here does not, like, if we only had these two, that would be fine. We could still do this, that's fine. However, if we want to apply the ideal gas law, right, remember PV equals RT, to be able to have other versions of this equation here, for instance, if we want to have a relationship between temperatures and volumes, so then I need to apply the ideal gas, and then I can get, for instance, temperature 3 divided by temperature 2 has to be equal to volume 2 divided by volume 3, and that is to the K minus 1. Okay, but I can only have this if I have an ideal gas, because what I'm doing is precisely I'm substituting where I have my pressure, I'm substituting by volume, mass, R, and T. Okay, we've done this before in the channel. We can have a look on previous problems. I'm not going to do it now, so we're just going to go straight off and use these relationships here. Remember that we have the relationship between the temperatures, we have that, and we're looking for a relationship between the volumes. So this is an ideal equation for us to apply. The T3 we happen to know that is the 310 Kelvin, and T2 is 500 Kelvin, and that has to be equal to the ratio between my volumes. I don't know any of the volumes. I'm just looking for a relationship between them. And K, if it's at 300 Kelvin, like it said in the beginning, is just 1.4. So this is just 1.4 minus 1. Okay, so that gives me that my V3 is 3.3 times V2. Okay, this is what I'm looking for, a relationship between the two. I don't know V1, I don't know V2, I don't know V3, but I know that V3 is about 3 times the volume of V2. Okay, and we can do the same thing for as we're going from 4 to 1. Okay, we're going to apply the same idea. So T4 over T1 has to be equal to volume 1 divided by volume 4 to the K minus 1. If you want to, you could flip this. You could say, okay, but you did the final minus the initial. That's fine, 100% fine, not a problem. You're going to get exactly the same result. So if you want to do this, 100% okay, no difference. Okay, so therefore T1 is 500. My T4 is 310, and I'm looking for a relationship between precisely my V1 and my V4, and this again is the 0.4, right? The 1.4 minus 1. And again, what I get, remember there's a lot of symmetry here going on. I get that my V4 is 3.3 times my V1. Okay, what I'm going to do now is I'm going to take a step back and see if this makes sense. If I indeed expect my V4 to be greater than my V1 and my V3 to be greater than my V2. So let's go back to our diagram. Here it is. Okay, we just found, probably want to do it again so it's not that messy. Here you go. Okay, so we just found that my V4 is greater than my V1. Let's see if that checks out on the diagram. So I would read my V1 down here. So this would be my V1. And I'll read my V4 down here. So this would be my V4. And indeed, you can see that V4 is indeed greater than V1. Okay, it's definitely not 3.3 times because my drawing is horrible. So what we get from this is that, okay, it makes sense that V4 is greater, but it also makes sense that Pablo cannot draw because this is way out of proportion. Likewise, we can read, we just found that V3 is 3 times V2. So we can read V2 here. And we're going to read V3 here. Okay, so indeed V3 is greater than V2. Again, probably not 3 times. It should be 3 times the value, but it's greater. Okay, so it checks out. It makes sense. Well, if I found it makes sense, it's good to do these, stop and think about what we're doing to make sure it makes sense. All right, so remember, the reason why we needed all this is because we wanted a relationship between V3 and V4 so that we can find work. Where is our work calculation? Here it is. Okay, and I've just found that V4 is just 3.3 times V1, so I'm substituting by that, and that V3 is 3.3 times V2, substituting by that. And then obviously these guys go away, but there's one thing else, right? We know that the relationship between V1 and V2, we know that V2 is just double V1. So in other words, we can, I'm going to do this, rewrite, I guess. Okay, I rewrite everything. So 287, 310, natural log of, and then we have V1, and we have V2 have 2 times V1. So this is natural log of 1/2, right? Okay, so now we have the two work per unit mass, and that's what we're looking for because that's what we want to find as our work output. Okay, so I can calculate the values here, or I can plug everything in, and I can sum everything up. And what I'm going to have here is like, okay, this is my 287, 500, natural log of 2, plus 287, 310, natural log of 1/2. Right? So what's this? Obviously, in magnitude, this is going to be the same value. Just it's going to flip the sign, make one negative. And the output of this is, number-wise, I got 37.79315. It keeps going, so 37.8 should suffice. 37.8 should suffice. Unit-wise, we haven't looked at the unit, but we can do that quickly because unit of this guy here is kilojoules per kilograms per Kelvin. Unit of this guy here is Kelvin. And this guy here has no unit, it's dimensionless, right? So no units for this guy. So this is dimensionless. And this happens to be, so we obviously Kelvins go away, and we're left with kilojoules per kilograms. Does that make sense what it does, right? Because we're looking for a unit of energy in the beginning. We're looking for a unit of energy in the beginning. And then what we ended up finding is a unit of energy per mass because we didn't have a mass. So I should actually include these guys here. Okay, so this is kilojoules per kilograms. And this is per cycle, right? Because this is when I do one cycle. Remember that how we got here? We summed up the 1 to 2, the 2 to 3, the 3 to 4, and the 4 back to 1. So this is one cycle right here in the corner. This is per cycle. Okay, and remember that this is not what we're looking for. This is just part of it. Because what we're looking for is how much mass I need to output 1 kilowatt. That was the question. That was part A. How much mass do I need to output 1 kilowatt? So to find part A, so I need to find mass for 1 kilowatt if 5,000 cycles per minute, right? So all we're going to do is we're going to look at the information that we have. We know that the work output here per unit mass is the 37.8 kilojoules per kilogram, and this is also per cycle. And I know that I have 5,000 cycles per minute. That's how fast this guy is spinning. And if you look at this, we're going to get rid of the cycles, but we're going to be left with kilojoules per minute, right? And that doesn't really help us out, so I'm going to go ahead and convert this into seconds. So I'm going to do 1 minute has 60 seconds, and that's going to give me kilowatts, which is what I'm looking for. This turns out to be 3,149.8. This is kilowatts, which is kilojoules per second, divided by kilograms. And my question is precisely how much do I need to get 1 kilowatt? So if 1 kilogram gives me all this amount of kilowatts, if I want just 1 kilowatt, I just need to flip this and see how many kilograms I'll need for that, right? So I don't know how you prefer to do this. There's a couple ways we can say precisely that 349.8 kilowatts is what we get if we have 1 kilogram of mass. So if we just want 1 kilowatt, we can just do the proportion, right? To divide by this value, so we divide by the same value here, and we get the mass needed. The other way you can do is just you can say, okay, work output divided by the mass. But what I'm looking for is precisely the opposite. I want to know how much mass per work output. So you can just flip this. So I'm just going to take the value 3149.8, and I'm going to flip this. Either way, whatever works about, what we're getting is the amount of mass per unit outputs of work. And this is 3.175 times 10 to the minus 4. Units obviously flipped as well, so this is the amount of kilograms that I need for 1 kilowatt. And that's the answer for A. Cool. Now that we have that, we can move on to B. Remember, B is asking us for the lowest pressure on the cycle. The lowest pressure on the cycle we found out in the beginning, this is P3. So this is asking us, what is P3? And now that we have defined most of the cycle, this is quite straightforward, right? Because remember that the thing that we do have is P1, right? And then so we can use P1. I might grab the diagram once again. The one that I didn't draw over. Here it is. Okay. So what I'm going to do now is I have P1, so I can use P1 to calculate P2, and I can use P2 to calculate P3. Another option would be you can use P1 to calculate P4, and then P3. That would also be valid. Okay. So what I'm going to do is from state 1 to state 2, from 1 to 2, we have an isothermal. So remember, P1 V1 has to be equal to P2 V2 because MRT is constant. Right? So this is just from the ideal gas law. And then in this case here, we know that P1 is, what is it, 350? Yeah, 350 kilopascals. And we know there's a relationship between V1 and V2, which has to be equal to V2. And because this is double this, that means that my pressure is going to be half the pressure of P1, right? So my pressure on P2 is simply 175 kilopascals. That's straightforward. Cool. With that, now we can go ahead and do the next step, which is from P2 to P3. And to do that, we can do exactly the same idea we did before, because again, this is an isentropic process. This is an ideal gas, and we're considering CPs and CVs to be constant, right? So again, we can actually copy and paste so that we're sure we're not making stuff up. This is the relationship here. We're looking for P3, so that means that P3 will just be P2 of V2 divided by V3 to the K. We know everything, so we can just be happy about it and calculate it. We don't know V2 or V3, but we know there's a relationship between the two. We know that V3 is 3.3 times V2, and we know K is 1.4 if we're considering CPs and CVs at room temperature. So this is away. We're left with numbers, which makes us happy. And we get this is 32.8941. It keeps going, so I'm going to go ahead and approximate this to 33 kilopascals. So approximately 33 kilopascals. And that is the answer for part B. And then part C asks us for the heat added and the heat rejected per cycle. Okay, so if we go, so part C, what is Q in and what is Q out? And this is very straightforward for us. Why is that? Because remember that Q in happens as we go from, so we're going from state 1 to state 2, and Q out happens as we're going from state 3 to state 4, right? The characteristic of both these guys is that it's an isotherm, right? Isotherm. And this is also an isotherm. What does that mean? Well, it means that if it's an isotherm and we're dealing with an ideal gas, you might recall that delta U is only a function of temperature for ideal gas. Yeah, we talked about that before. But if it's only a function of temperature, then if I'm dealing with an isotherm, remember, again, we can do the same thing as we did before. Let's keep the color code here from 1 to 2. So 1 to 2, I can do CV times delta T. However, delta T from 1 to 2 is the same because they're both at 500. So this delta T here, CV from T2 minus T1, this has to be 0 because they're both 500. So that means that my delta U is also 0, is nil, right? Likewise, same thing happens as we're going from 3 to 4. Same exact thing, right? We're dealing T4 minus T3, but they're the same temperature because it's an isotherm transformation, so this is nil. So this means that this is also 0. And if my delta U is 0, what does that mean? Well, it means that because of the first law of thermodynamics, it says that delta U equals Q work, and if this guy is 0, then the magnitude, splitting magnitude for simplify things, magnitude of the heat is the same as the magnitude of the work on this isothermal process. Okay, so, and we found the work already. We found work from 1 to 2. We found work from 3 to 4. So we can just use that, right? So again, heat addition heat in equals work from 1 to 2 because of this. Okay, and unit-wise, we're going to talk about that in just a second. And we know that this is the 287 that we found before times the 500 times the natural log of 2. We did all this math before, and we found this guy to be 99.5 approximately, right? So 99.5 approximately. And this is kilojoules per kilogram. Okay, so this is heat addition per unit of mass. And this is the heat addition. Likewise, the heat rejection, Q out, in magnitude is going to be the same thing as the work being used from 3 to 4. Okay, so let's just leave for now 3 to 4 here. So heat from 3 to 4 equals work from 3 to 4, and that is the 287 that we used before, the 310 we used before, and the natural log of 1/2 that we had before as well. And this is approximately 61.7. Negative 61.7 because this is a negative value here. Okay, so there's two ways we can write this. The negative value is telling you this is being outputted. The other ways we can just say Q out equals 61.7. Okay, because what this is saying and what this is saying is the same thing. So this is telling you that heat is being outputted from the cycle, and then if you write Q out, it's already implicit, obviously, that this is being outputted from the cycle. So that is our answer. Obviously, because this is a cycle, we had another option, we had another alternative, right? The alternative was that we could have found either of these. So we could have found Q out, for instance. You can find Q out by relating the work, because we know the work output on this cycle is just the difference between the heat that's being added and the heat that's being outputted. So the work's actually the useful heat, let's put it that way, because whatever's not being rejected is being used as work on this cycle, right? So again, we had the information. We found already the work output for this cycle, the work per unit mass, and that was 37.8. So you could have written 37.8 equals the 99.5 minus Q out, right? That's also a possibility. And then obviously the value will be the same. Q out equals 61.7. Okay, so that's the amount of heat being rejected in this cycle, in this ideal Carnot cycle. Hopefully this was useful and understandable. If you have any questions, let me know, and we'll talk.